Okay, well, it's a pleasure to be here and to enjoy the nice weather here when it's raining in the Netherlands. So I want to tell you a little bit about some recent progress in track functions. And I want to start with actually giving you a little bit of a motivation. So, well, why do we want to do track-based measurements? Or why do we want to use tracks in measurements? It's because we have a very good angular resolution. And so it's particularly interesting if you want to look at things at small angular scales. And so for jet structure, it's very helpful. An extra thing you get as well is that you can trace back which vertex the particles came from. So you also can use this for reducing the pileup. And to make this a bit more concrete, you can actually also see this in this example. This is for a groomed jet mass, a measurement based on calorimeter versus tracks. And of course, the first thing to highlight is there's data in here. That's the gray band. And you can see the uncertainties on the data become much smaller. And in this region is mostly from pileup, but you can see that basically everywhere the uncertainties are smaller when you do the track-based measurement. Another thing to notice is that this is compared to different Parton showers, and you can see that the spread between the different showers is actually bigger than the uncertainty of the data. And so, well, having motivated looking at track-based observables, and also seeing that there's this difference, you can ask the question, can I do something else to describe track-based measurements? And that's what I want to tell you about today, which is a formalism we developed. And basically, formalism centers around track functions, which allows you to describe the effects of converting particles to tracks in a very similar way as using Parton distribution functions or fragmentation functions. And we recently extended this to order alpha squared, which means you can also do, not just say, okay, we can do some calculation, we can compare to Monte Carlo, well, we're maybe on a similar level. You can now imagine actually doing a much more precise calculation. Of course, this track function that I'm describing is a new normative object, and that means that you need this in your calculations. It is being extracted by Atlas, and so I do expect that soon we actually have some track function that we can use that's not extracted from a Parton shower, because that's what we work with right now. But I should also emphasize that it turns out that for a specific class of observables called energy correlators, the way you use tracks or do a track-based measurement is very simple. So it's very easy to incorporate tracks, and you only need not a full track function distribution, but you only need a few numbers, namely some moments of the track functions. Anyway, we're going to see this in a bit. You could get the quark track function from that data. The glue one probably will not determine very precisely. Yeah. It still might be useful as a reference as well. Yeah. Okay, so sorry, I clicked a little too fast. This is the outline. I'll talk a little about the basics for track functions. Then I'll talk about extending things to order alpha squared and what we did there. I will not show you all the details, but hopefully enough to explain how we did this. And at the very end, I want to talk about some of the phenomenology. So to get started, what is a track function? It's a normative object that describes how a quark or gluon gets converted into charged particles. And it's not that we're asking about individual charged particles, we're actually asking about the momentum fraction x of all the charged hadrons. So here you see some hadrons drawn. The red ones we imagine are being charged, and we actually want to know what's momentum fraction of these compared to the original quark or gluon. And so this is a normative object, just like a PDF or fragmentation function. It is also universal, which means you can extract it from some measurement and apply it in another one. But it's different from PDFs and fragmentation functions in, for example, that we have this sum rule, which is the conservation of probability. And it arises because we're asking for every final state, we get one momentum fraction. So with fragmentation, you get multiple hadrons. Here we just have one momentum fraction of charged hadrons for every final state. And for completeness, I also put in the definition. And well, this is the definition in terms of some matrix elements. And it looks very much like the definition of fragmentation, except that we're measuring here is not the momentum fraction of a hadron, but that of all the charged hadrons in the intermediate state X here, or in the final state X. Okay. So with this, it's proportional. Well, but again, like this is up to order lambda QCD, so we're imagining things are very energetic. And so in this definition, I could have also worked with say, a ratio of energies if I wanted to, but then if I want to do some nice power counting, this is the more clean observable or clean way of defining this. Yeah, that's why there's a minus momentum here, which is, by the way, the large light component momentum, given that we all use different conventions for these things. Okay, so we have a definition, and so you can go ahead and calculate this object, at least when you are doing this partonically. And so you find that it's 1 of order alpha s. You actually can interpret this as kind of a splitting. And so you find that you get indeed the splitting function appearing. You also find that you get track functions for the 2 branches that appear here. And there's some delta function. And this delta function essentially says that you're summing the contribution of both branches, because we are really asking what's the total momentum fraction. There's a UV pole and an IR pole. And this part of the story is very similar to like PDFs or fragmentation functions. The IR pole will cancel when we calculate a partonic cross-section. There will be some other IR pole that cancels this one here. And the UV pole gets renormalized, and that actually leads us to the track function evolution. So the picture for the track function evolution itself is very similar to this picture that I draw here. I mean, the equation barely changed. I got rid of the UV pole and I got rid of the IR pole, but essentially it's the same equation as the previous page. And now the derivative with respect to the renormalization scale. And so this is a nonlinear evolution equation. Well, there's a few things to say here. First of all, this is only at order alpha s. And so what we'll see later at higher orders becomes more nonlinear because you'll get more and more track functions appearing. So once you start at order alpha squared, you get 1 to 3 splitting contributions. So you also get terms with 3 track functions on the right-hand side. What we did at this, and this is already almost 10 years ago, but what we did back then is we just tested consistency because we had no track functions to work with. So we extracted track functions from Pythia at different scales. And these are the different colored lines. And then the black one is what we kind of took as our initial condition. And then we evolved this to different scales, which are the solid orange or the solid blue. And we compare this to the extraction from Pythia at these different scales, which are the dotted blue and orange lines. And things look consistent. So that was at least reassuring. But at this point, we're not going to claim that we're doing anything better because we're using the track functions from Pythia.
Just for me to understand, these are the regular
Yes.
That are basically the random link.
Yes.
So how can I use them for the solution where, I mean, should I think of this like being the longitudinal fraction of the momentum? Because the exit was the actual ratio of the full momentum. So that's why I'm confused.
Okay, sure. So I should go back for a moment. And I should say that what we're doing here is that really, it is the ratio of the longitudinal momentum, but the way that we interpret this, and this is also what will come up when we try to use track functions like to calculate some observable, is that really the charged hadrons we are imagining are still moving in the same direction as the original particle. So that's why I write this, even though it looks like 4 momenta, with just 1 x here. Yeah. And of course, it depends on the details of the observable, whether this is a good approximation or not. But yeah. But even in the case where you have wide angle soft radiation, what then happens is that you can calculate that soft radiation perturbatively, and then at the very end, you can tag on a track function in some sense. So you can say, oh, I have a soft emission there. It is far away from other things, but still there. If you calculate to a higher order, that soft emission would still have a collinear singularity, and that has a corresponding track function. So I'm not saying that all the radiation will look essentially. Ooh, I'm not sure what happened here. I guess the internet connection. Let's try this again. And where is it? Or did the thing crash? No. Okay. There we go again. Yeah, so I'm not saying that we have one track function that describes a full jet. Actually, you'll get multiple particles in your jets, and unless you have a measurement that resolves them to be separate from each other, like, well, okay, maybe I should talk about this when we get to the actual, how you include track function calculations. That's maybe a bit easier than, oh, it is working. but it's not changing on that screen. Interesting. No, it's the internet connection. Okay. I've had many Zoom calls here already, but not any with as many issues as this time. Now it works, and hopefully will stay working. One other thing to point out, so normally we're used to, for the PDF and fragmentation function evolution, to take moments, because that makes things easy. Here it turns out you can also take moments, but only integer moments become easy. Because if you integrate this with an x to the power n, then this delta function just becomes this thing here. And only for integer n you can do some simplification, because then you can use the binomial expansion. I guess technically you can also do it for non-integer n, but then you get infinite zero. Very useful. Okay. So I also wanted to compare maybe more explicitly how does the track and the fragmentation functions differ from each other. And so here you can see this. There's a delta function that says the momentum fraction is the sum of the two branches, and then they are rescaled because in each branch the x1 and x2 are again with respect to those initiating partons. So that's why you have these rescaling factors. If you compare that to how you do fragmentation, then you say the hadron comes either from this branch or from this branch. I sum over both possibilities, but I get a similar rescaling factor. So this is how you could compare the delta function that shows up in the track function evolution versus the one that shows up in the fragmentation function evolution. And because in the fragmentation function evolution, you only really pick out one branch, that's why you get a linear equation with only one fragmentation function, where here you get something that's nonlinear. And so one of the things that we also show, not just as pictures, but also with actual equations, is that the track function evolution allows you to derive DGLAP. Well, it's probably not so surprising, but also like the evolution of multi-hadron fragmentation. So if I schematically draw my evolution kernels as some blob with the red dots indicating how many track functions are on the right-hand side of the equation. So far you have maybe this term. Well, this you can, if you want, you can reabsorb this into this. But anyway, if this is your picture, you can now say for single hadron fragmentation, then the hadron actually comes either from this, well, here it comes from this one, but here it comes from this or this. And with the three cases, it comes from one of these lines, and that's basically what's pictured here. So, and you can literally just take that evolution kernel and get back the DGLAP equation that way. But you can also do the same for dihadron fragmentation, where you can say, oh, the dihadrons are coming actually from the same parton, and that's where you get like a picture like this first row here. But you can also have them coming from two. So that's why the dihadron fragmentation function actually has an evolution that involves both a dihadron fragmentation function, but also two single hadron fragmentation functions. So in this way, you can see that the evolution of the track function and of multi-hadron fragmentation function are very much related. They're all going into the same direction of that original parton, yes. Yeah. Well, we are restricting ourselves to observables where you say, I'm going to measure, say, thrust, energy correlator, something like this, and I'm going to say, now I'm going to measure the same observable on charged particles. So I'm not really asking about, can I measure all the individual charged particles? I'm just asking some relatively inclusive measurement with maybe resummation, but I'm then applying that to charged particles. So I'm not at all trying to make a parton shower, if that's what you're asking.
One of the rules is plus positively charged and other is negative, but they are end up in the same color.
Yes.
Maybe the magnetic field.
But the thing is, the whole point of these track-based observables is that you want to actually measure them with the tracking and not with the calorimeter, right? That's where you're getting your great angular resolution for jet substructure. And I will have a slide where I show you how you can get track functions from the LHC. So I will also make this more concrete. So how would you measure the track function itself? But basically, it's measuring the momentum fraction of charged particles in a jet. And that is a leading order just a track function. And of course, if you go to higher order, you get perturbed directions. oh, I don't have to know that. So you are worried indeed that I need to know at the microscopic level from like where they come from. But if you think about how we get fragmentation functions, we also do not ask exactly where it comes from. We just have a formula that says this is the cross-section for fragmentation. I now measure fragmentation, and I can infer by using this formula for the cross-section what the fragmentation function is. I don't actually have to resolve exactly did that fragmenting particle come from exactly this point. So it's very similar in this case. But the fragmentation function evolution, you can have a very similar picture as for the track function evolution. Sorry if I'm making this maybe more complicated than is necessary. Okay, so now let's talk about how you actually do this in calculations. And this is maybe a little bit too simple here because I'm restricting myself mostly to leading order. But imagine if you're doing some leading order calculations for some observable. You have your squared matrix elements, you have your phase space, you integrate, and then you pick out your measurement with the delta function. At leading order, if this is like a leading order calculation, what you will do to do it on tracks is that you say, oh, every particle I'm producing actually will get converted to charged particles. And therefore, I get a track function for each of them. And I will integrate over the momentum fraction of this momentum fraction. And then I say, well, how much of my original momentum is then in charged particles? It's x times that p that I had before. That's basically what I said in the first slide. Like this track function describes how much of this momentum is going to charged particles. This is the leading order picture where everything, of course, is well separated because I don't have any collinear divergences. You can, of course, repeat this story at next leading order. Then you will find that you get, of course, the collinear divergences, but they exactly cancel against the IR pole that I showed before for the one loop track function. So you do the same kind of cancellation as you have for fragmentation functions or PDFs, and you get some finite cross-section. So this is the more complicated case, actually. So now I think I will tell you about why energy correlators are nice. So here's a picture of what an energy correlator is. And basically what you're doing is you're taking 2 points and you're fixing the angle between them. So that's this chi that you have on the left-hand side. And you're saying, if I have 2 particles, or I have 2 directions, 2 particles, if you say this, like how you do this at LHC, and they have this angle that's equal to this, then I get a contribution to my histogram, but I weigh it by their energies. Because you divide it by q squared. And so this is something you can measure, but if you're going to try to do this at small angles, there's no way of doing this without doing tracks. But the nice thing is, here the conversion to tracks is very simple. Because basically, if you have an energy and you want to know, well, I convert this to charged particles, then I just rescale that with the x, and then I integrate over the track function. But this is simply just the first moment of the track function. Again, people have different conventions for moments, but this is what I will call the first moment. And so in this example, and honestly, this case you could have done also with a fragmentation function, because you're just talking about hadrons being produced either here or here. But if you now look at the contact term where this angle becomes 0, then you actually find a contribution involving the second moment of the track function. And if you generalize this to endpoint energy correlators, well, you say endpoint becomes very complicated because they have lots of angles, but you can also look at projected endpoint correlators where you integrate over all angles and just put a restriction on the maximum. Then you end up getting that this is depending on the nth moment. So for the endpoint correlator, you need up to the nth moment of the track function to describe this. And one of the things that I just want to mention is, like, since you have now anyway gone into this game of doing tracks and requiring non-perturbative information, it turns out you don't have any extra penalty to modify this energy weighting. So in the original energy correlator, you basically are stuck with that this n is 1, because otherwise you're no longer IRC safe and you cannot calculate in perturbation theory. Since we already have let this go, then there's nothing extra. Like it doesn't cost us anything to change this n. And there's also reasons to do this. So this is a picture I stole from a paper where they proposed using the 3-point energy correlator to look for, or to determine the top quark mass. And basically, I want to highlight here that n is 1 versus n is 2. And so n is 1 is these top lines, n is 2 are the bottom lines. And you see you get a much nicer peak if you change this energy weighting, because you're just suppressing soft radiation more. Okay, so that was the basics. I want to tell you a little bit about order alpha squared. And I basically have one slide on the calculation, which has mostly just text and not so much equations. But I'm happy to discuss this more. So we have a definition of the track function. And so if you want to, you can just start calculating with it. But we already saw at order alpha s that you get 0 because it's scaleless. And at order alpha s, it's not so hard to pull apart UV and IR divergences. But it didn't seem to invite us to try to do this at order alpha squared. And so what we did actually is to calculate something different. We decided to calculate this jet function that's differential in an invariant mass and the momentum fraction of charged particles. And this is the invariant mass of all particles, not just specifically charged. And so it turns out that this thing, I mean, now you have a scale because you're measuring this invariant mass, so you can calculate this thing easily in dim reg. And the UV poles we actually know from consistency. So these UV poles are the same as if you just have a jet function where you only measure the invariant mass. And the consistency I'm referring to is that if you have the factorization theorem for thrust, these jet functions appear. And if I would now also measure momentum fraction of charged particles in one of these directions, then I would get this jet function, but it only changes this one jet function. It doesn't change the soft radiation because that doesn't contribute. It means it's a power suppressed contribution. So anyway, I can calculate the thing. I know the UV poles. And so from the remaining IR poles, I can actually get the track function. And for this, I use this following matching equation. So the jet function that we've calculated, you can actually match onto track functions. And this is done at the renormalized level. So we've now calculated this. This is the thing we want to get. And then you have all these perturbative corrections. If we only want this piece, we can just focus on the delta S contributions. So that's why I only wrote down those kind of contributions. And also the track function, we now have the renormalized track function. So we have only purely IR poles, which means I can also get rid of this second line actually, because this is IR finite. Because this is like the leading order track function, which has no poles in it. And so basically I calculate this, I subtract this piece, and then I'm left with the track function I want. And again, because of the fact that these are UV and IR poles, knowing these IR poles is the same as knowing the normalization group equations. And so we get these two things at once. And I guess there's always this, okay, here it is. So this is the evolution equation, at least its form at order alpha squared. So previously we had a term involving two track functions. And if you want, you can also separate out a piece with a single track function. It's basic where there's some delta function piece in here that you can move over there. This is the structure then at order alpha squared, where there's now also three track functions. And these evolution kernels we've calculated. And I've plotted them here. So, I mean, there's basically like three momentum fractions, but they're constrained to be total of 1. So that's why I'm only plotting 2 here. And this is for the gluon going to gluon and a QQ bar. This is a quark going to a quark and an anti-quark pair of the same flavor. But if you actually want to use these expressions, we have made them available electronically. They're also in our paper, but typing them up is like 10 pages. Probably not too inviting to do it that way. And the D is a finite integral over these things because everything is like regulated at this point. So that was at some level like the complicated thing. Like when you calculate this jet function, all the angular integrals you can do, but then you still have something that involves two momentum fractions that you want everything properly regulated. So that's why, yeah. So this is then in some sense, you only have to now do a finite integral. Okay, so now you can also see how much does this do. So this is the track. This is similar to a plot we saw before for the track function evolution. Again, the initial condition is at 100 GeV, but this time it's orange. And the left plot is for the quark track function, the gluon track function on the right, and evolve up and down. But now I'm comparing the leading order evolution and the NLO evolution. And I don't know how good your eyesight is, but at least for the quark, the difference is not that visible. For the gluon, it's a little bit more visible, right? You can see there's some differences here. So it's a small correction for this evolution, which is, I guess, also a good thing, right? It means that not a dramatic change. Maybe I should have made this comment earlier, but this evolution, of course, looks quite different from the linear evolution for DGLAP or that you have for fragmentation function PDS, where you get these really steep behavior in momentum fraction X. Here, actually, everything is pretty mild. And the evolution code, which you did 3 different ways, you can also find that online. Okay, so let's do some phenomenology with this. And I see, okay, I think that's, I'm also not, this is the last part and just some plots mostly and some discussion. So this was the first application we looked at. And this is also the reason why we didn't do anything on track functions for a while after we did this application. So maybe I shouldn't have shown it, but I do feel like for just the historical picture, I should include this. So this is thrust on tracks. This is the Delphi data that's shown here, the tracks and all particles. This is the Pythia plots, and this is our calculation. And it turned out that you can do this. I mean, the calculation is a bit tedious because you have to put in track functions everywhere, but it can be done. But then when you look at the plot for all particles versus tracks, it's a bit disappointing because there's almost no effect from the tracks. And so that's why we're like, okay, well, yeah, indeed, also in Pythia and in the data, the difference is mostly really in the peak. And that's exactly where there may be additional non-perturbative effects that we don't understand and how they would interplay, or what their interplay is with the conversion to tracks. So at that point, we're like, okay, well, it can be done, but why should you do it? I should also maybe say that it's not that we just did this and then we say, oh, it comes out and this is what the answer is. It's also that we actually understand there's some accident that happens between the quark and gluon track function. There's some cancellation. So some moment appears that you have to calculate, and it happens to just be accidentally small. So if you just make up some toy quark and gluon track function, you normally get a much bigger effect. And actually, I'll return to this point when we talk about energy correlators. Yes. Yes. Yes.
Could you use total?
I mean, you could divide by the total, and then you would see some effect, which is going to be roughly the same as rescaling with the track function. But the thing is, this is what we had data for. That's the Delphi plot. Oh, and it's kicked me out again. So that was the reason why we picked this one. This is an example of much more recent dates. So this, I think, is like 2 years ago. And this is an example where the effect of tracks is almost 0, but it's also for a reason we understand rather than a reason we don't. Well, that seems accidental. So the observable that we're looking at here is the azimuthal angle between a vector boson, that's this green thing here, and a jet. And so you're looking at the angle in the transverse plane. And normally they would be almost back to back, but then there's of course some collinear and soft radiation that causes it not to be like that. And if you use a specific scheme, a recoil-free recombination scheme, it turns out that the only effect of doing this measurement with tracks is going to affect your collinear radiation, not your soft. And so as a consequence, it means it doesn't show up in any anomalous dimensions. It's actually going to show up in your constant pieces. And so it's beyond next leading log. So you expect to be very small. And indeed, if you do this in Pythia, you can try both options and you see something that's basically consistent with the statistics we had. And maybe you can say that there's like a % difference really at the end, but that is a very small difference. So maybe to move on to like more interesting cases, because we saw a case where it was accidentally small. Now we saw a case where it's small. There's also a case like these energy correlators where it is really not small. And I guess I don't have the plot here that shows it with or without, but you just get a rescaling because of the fact that you get converged to tracks, and therefore the energies are already going to be smaller. This is the asymmetry of the energy-energy correlator, which is defined in this way. And this is also where we found data for it that we could understand. And shown here is the data compared to our predictions at leading order and next leading order. And so the thing that we were quite happy with is to see the reduction in certainty, the bands that are overlapping, and also the agreement with the data that looks just quite interesting. So this is the plot for Zoltan. Since you asked before about how you get track functions, basically what you can do is you can look at your jet, measure the momentum fraction of charged particles in the jet. So then you need to know the total energy in the calorimeter, but you don't have to know which of that was charged particles, and you measure your the energy of the charged particles. and you take the ratio, and that distribution is basically the track function. And so here we have some prediction compared to Pythia for some kinematic bin at the LHC. The plot on the right, I've included to show you that there's also a non-trivial effect from the JET algorithm. So you can, of course, measure this, and that's also what they're measuring. But if you actually want to know what is the underlying track function, then you say, well, I can take a leading order picture and just say, this is the track function. But I can also take a next leading order picture where I say, well, there's actually some perturbative radiation, and then I apply the track function. And you can see that that shifts things a bit. So here we have plotted are where it says track. So the purple and the green, those would be these are just directly the track functions. Whereas if you include the effect of the jet, you get a slightly different distribution. So those are the blue and the orange that you see at the bottom here in the middle. So this is just to say that there are effects from doing this in a jet that you have to take into account. Okay, so moving on to the endpoint energy correlator. What we're going to look at is a projected energy correlator where you integrate over all angles, but you fix the largest angle. And what is plotted here is not directly the energy correlator. I'll show that actually in the next slide, but I'm plotting the ratio of charge to all. And this is a function of this angle. So this is, as you go to the left, it becomes more and more linear. And one of the interesting things you see is that for the 2 point, this is almost a constant. And this is a part we can directly calculate with track functions. Here it is some free Hadron regime where you can also predict that it actually should go like this. And so it just goes straight through. And this is at some level also maybe how you can interpret what we saw for thrust, because it doesn't really probe like 3-point correlations. And therefore, it's just some overall rescaling. But interestingly, if you look at these higher point correlations, you actually get some non-trivial behavior. So here you find like for these 3, 4, 5, 6-point correlators, you get a different behavior. And on the right, we also show our calculation using the track function of Pythia to just kind of compare. At some point, at some point, you're essentially probing a scale that is like x times q squared. And so at some point, you really get into a non-perturbative region. So that's the reason why, I guess this is also like, here there's a power law, which we can calculate. Here there's a transition, and here you're really in a like everything is just hadrons. So you're looking at correlations between hadrons. So that's why, we have predictions, but they become less and less reliable as they go into this region. Yeah, this is a transition, right? So this is a region, this is where we understand things. Here we also understand things, but it's like purely non-perturbative physics, but at least we can still simply understand it because everything is just free hadrons. Here's some intermediate regime where we don't really know, and you can just, of course, draw a line between the two. And Pythia does that very efficiently for us, but we don't have how it should be done. Okay, so here are actually the ratios of endpoint correlators to 2-point correlators as a function of this angle. And again, shown as Pythia, which we just plot everywhere, and our analytic predictions. And the left plot is for all particles, the right is for the charged particles. And just 2 points to make, which are already on the slide here, is the behavior is qualitatively similar. So the dependence on the slope as you go to higher points increases in both cases. But if you look actually at the quantitative, like the numerical values are quite different, right? So here it goes up to 20, this goes up to 6. So you can see that the range you get is quite different. But the point here is that we can actually calculate this. And well, you can say maybe you don't have perfect agreement with Pythia, but at this point we're also like, we only have Pythia track functions. We're using Pythia as like the proxy for the real data. We'd prefer to have real data to try to push for further agreement rather than this is, so here, oh, sorry, I didn't say here, this is next to leading log. Yeah, so we didn't do any matching to fixed order, but we do next to leading log. Yeah.
Do you have an understanding what it is that they actually found? Like, you're satisfied, but more than right hand of the
Sure. I mean, this is the fixed order region, and we don't match the fixed order. So if you look at this plot, this is the collinear region. I mean, this is all this kind of non-perturbative collinear region. This is the perturbative. Sure, but it is at least filling that region of phase space in some more sensible way than we are, right? So if you look, for example, the thrust distribution, and if you do a resum calculation that's really strictly expanded, then you get something completely crazy. If you go into the fixed order region, basically does something sensible. How good it is of course.
Would expect this to go up.
I have to be honest, I don't actually know if I necessarily would expect it. I would certainly expect it to be different there. Yeah. So, okay, I think that's almost it. Oh, and I want to briefly highlight. So we looked at correlators, function, all that. The only point that I want with this slide is that you don't have to just restrict yourself to tracks. You can also say, let's look at charged particles, positively charged particles, or negatively charged particles. And that you can, or even look at charge-weighted energy. So they, this is Ian and Kyle, and they've actually looked at this more general energy correlators. So for example, in this right plot, this is like a 3-point charge-weighted energy correlator divided by just the track-based one. And well, you can literally see back then the charge of your jet you're looking at. I'll be honest, like I don't have a good intuition for like what's the most interesting thing to do with this, but at least it's something that you can do. You don't have to stick only to looking at all charged particles. And so that already brings me to my conclusions. So why do we do tracks? Because of the good angular resolution. And this is particularly interesting for things like energy correlators, where you really probe small angles. The track function formalism we've extended now to order alpha squared. And the evolution equation you get is actually a very general collinear evolution equation, because you can project it down to go to DGLAP, but also to like dihadron fragmentation functions. And then I showed a couple of applications. And in particular, the energy correlators are very nice because you add the track functions, it's very simple. You just have a few moments you have to do. So thank you very much.
We had plenty of questions already during the talk, but please. Yeah. So, how do you use this function in a calculation, in a cross-section calculation? I think you had a slide at the beginning.
This one here.
Yes. So this is kind of analogous, I would say, the fragmentation function for something like. So do we have such a factorization theorem at all order level?
It relies on collinear factorization. Did I prove that this works to all orders? I will be honest, I don't say I would have proven this to all orders yet.
So I think it's probably at the first order level it works. It's something like very similar.
Order alpha squared, so it's not like
it's
not, because at order alpha s everything works, right? That's also why I would not stand here as confidently if at order alpha s things work, because then, well, it looks good and it compares well to Pythia, but things also work at order alpha s squared. And we've also been looking at some of the moment stuff. You can push some things to order alpha s cubed even, because you don't need only a few moments for these energy correlators.
And don't you have to worry about soft gluons between the different directions? So in this, there is this delta function. I guess there is a sum over I, which
well, this is really this observable is like, it's a function of these momenta, right? So it's not necessarily a sum. Like for thrust, it's a sum, right? But you can also apply a jet algorithm.
Okay.
So if I'm trying to measure multiple hotspots inside a jet, then I just kind of wonder about the probability of crossover between the different hotspots. You're trying to treat cluster of partons in one direction and the track function based on that, but To some
think-
extent, they can cross over. Maybe you said something about this in earlier, but I'm not sure.
So I think the real question is, this will work as long as the kind of scale that you get to the hotspot is actually still perturbative. Once it becomes non-perturbative, then you can forget about it. As long as it's still perturbative, you can actually still calculate it and then match them to track
I
function.
could kind of imagine if I was looking at something that had very little energy in one hotspot and a lot more in another one, then I could get something that looks soft from the point of view of that hotspot, going over and making a big perturbation to the second hotspot. What do you have to say about that?
That's a fair point. So in this calculation, we always assume that X is an order one quantity. And of course, if you're really pushing yourself into a regime where you say, okay, so if you do an energy correlator and you always summon, then this such a configuration will be suppressed. But if you're really isolating this region, then probably you have to worry whether there's another scale that you have to resolve in your calculation. And I don't know. My guess is that if that scale is still perturbative, that you can still use track functions, but you will have to do more complicated calculation. Because then you, at some level, you will first do your calculation down to that scale that you have resolved. And then beyond that point, everything is again well separated and you can think of track functions. Yeah.
So I'm guessing that the track functions here are positive definite.
They don't, strictly speaking, have to be positive.
Okay.
Because it's, at least if you start including analog corrections, you can get like small negative contributions as well in some regions, but.
Okay, because that exactly was my question, because on page 18, it looked like there was a small corner that was negative.
Yeah, no, so that this can happen, right? Yeah.
But how does that then ensure that the left-hand side stays positive?
They still have to integrate to one.
I mean, I guess so. So in this example, this is like, so they need first they have to integrate to one, but also in this example here, I'm saying everything is like leading order, and so then you should also use a leading order for track functions, which do have the property that everything is positive, but only the NLO corrections would make that track function have like a negative read, but then also your perturbative correction would compensate this. Yeah.
I do have a question. Perhaps you mentioned, but I didn't catch that. I mean, do I have to think of the different? I mean, if I include the non-perturbative effects, do I have to think of a different track function for every possible hadron? And is there a? I mean, what is the strategy here to extract the non-perturbative part of these objects?
So you can, and this is what I try to hint at the very end. You can also define track functions for very specific things. So here I've always been talking about all the charged particles. I could also say I do this for pi plus only. I only want a track function for pi plus if I somehow can identify these very well.
Okay.
And the whole perturbative calculation part is
But because then if you define them for all possible charged particles, I mean, how universal is the non-perturbative part that you can measure in one thing?
But this is the point, like, at least here the incentive was not that I mean, at the LHC is not that we're going to talk about all these different charged particle species. We just want to talk about charged particles in general, right?
Okay.
That's what we want to use to study jet substructure. And like, unless you have a specific reason, you say, I want to have something that has, I don't know, a charm quark in it, and I want to specifically isolate that, then you can do it. I think also, and that was, I didn't mention this, but this slide where you say, oh, well, we can also do things with energy correlators on positively or negatively charged particles. When we originally did track function, we never thought about doing this because then in principle, you can get double differential distributions. But if you're doing energy correlators, you only get moments, and therefore this still seems like a feasible thing to think about. But in general, I wouldn't really want to do track functions that have all these different hadron species.
Okay.
Yeah. Because then in principle, but also the correlations between them.
I mean, how do you? I mean, we mentioned, but how do you get the non-perturbative part of this object? Is there a
for the track function?
Yeah.
So this was indeed a slide. Let's see this one here. I mean, basically, the measurement you do is you measure just the momentum fraction of all the charged particles to all the particles in your jets.
Mm-hmm. Okay.
And that's at leading order, this is really the track function. But then you can also take the full analog formula you need for that cross section, and you can extract the track function with the analog corrections accounted for. Okay. Just like with PDFs, right? You have
track function.
Yes.
Yeah.
The Atlas goes out and measures, you want them to measure the quark jet,
You want, or at least you want quark and gluon separation. Yeah. Sorry?
I mean, it's a little complicated because Atlas doesn't have a jet that says, oh, that's a quark jet, right? I mean, Walter told me earlier that they want to use, they do similar things when they try to fit to energy distributions inside jets. They use the PT of the jets as a measure of quark and gluon and then try to unfold that, I think. But they have to, they're supposed to be measuring this track fraction on jets fitting to some combination of the quark and gluon ones, I guess, right?
Yes. Yeah.
And then, yeah.
Somehow related question. I mean, when, for instance, we do PDF fits or fragmentation function fits, we consider the evolution and we start from a parameterization at a given scale, Q0, no? And I'm wondering here, I mean, you didn't speak about any parameter.
I did not, because at this point we've been using Pythia and we can get as fine a distribution as you want, right? Yeah.
So you don't introduce explicitly any parameterization here when you have the non-perturb. I mean, at the scale from which you start the evolution.
I think in the end we probably use some polynomial fits to get something a bit more smooth than just like the histogram from Pythia.
Mm-hmm.
But
you start as like, okay, you take as basis Pythia basically. So you trust Pythia.
Well, I trust
you didn't.
It is the best thing we have right now. So until there's actual data, yeah. I completely agree. I mean, this is at some level, this is the point of my talk, that there is a framework for doing this conversion to tracks that is not just Pythia, and that you could systematically improve.
Yes, but for instance, I mean, it's always in all the PDF business and also fragmentation function business, it's always very ambiguous, the choice of the parameterization, no? And we saw different fitters that use completely different parameterization, and at the end they, in any case, find something that more or less agrees with data. So I think it's important.
If you look at this shape and you compare that to what a PDF or fragmentation function is like, it is, I think, relatively easy, right?
Yeah, in that case.
I mean, the thing is, the evolution pushes this thing at some point to a delta function. And as it does so, it does it through a Gaussian. So it already looks fairly Gaussian at this point. Maybe
because it's just the sum of many different parts, so it's somehow unobservable that depends on many things. I don't know.
Well, so the evolution pushes you this direction, but of course, what your original non-perturbative input was, that is what nature tells us, and I wouldn't dare to say that at the loop school, it's certainly not as smooth as this. I mean, this is at the PT of 500 GeV. If you go down to 30 GeV, the jets look much more messy. Yeah.
Just connecting to this, so I guess you have an evolution for this track function is basically a MS bar based on an MS bar subtraction, and that leads to a kind of Diglop-like equation. So if you try to get out this track function from Pythia, that's what I understood. So how do you know that the Pythia actually provides the right evolution?
That I didn't know. And that's also at some level, all we can say is it's at leading, okay, then I should go back to the original plots where we do this kind of comparison. Here we just compared our evolution to essentially the evolution that's in Pythia from the Parton shower, and you find that things look very similar. Yeah, did it have to be this way? I don't know. It didn't have to be as good as it looks here. But at least instill some confidence, because this was our leading order evolution, and we now already have one order higher. So.
Right, I see no other questions, so let's thank Wouter again.